IE 141. Assignment problem. The assignment problem is a special case of the transportation problem. Here, the supply and demand nodes have a one-to-one correspondence. This is a special property of an assignment problem called unimodularity. Here, the values of the variables are only either 1 or 0. Remember that in a transportation problem, we can have a many-to-many correspondence. In assignment problems, the transportation simplex proves to be inefficient because of the high degree of degeneracy of the BFS. You can still use it, but most of the time, you will end up taking more time than necessary. That is why in this video, we are going to discuss the better way to solve assignment problems, the Hungarian method. Let us assume that we are given a minimization problem as our assignment problem. The steps in solving the LP using the Hungarian method goes like this. Step 1. Construct the cost matrix of the assignment problem. Step 2. For each row, find the minimum cost, then subtract this value to all the costs in the said row. Step 3. For the new matrix, find the minimum cost for each column. Subtract this value to all the costs in the said column. Step 4. Draw the minimum number of lines, both horizontal and vertical, that are needed to cover all zeros. If there are already m lines, an optimal solution was found to proceed to number 6. Otherwise, proceed to step 5. Step 5. Find the minimum cost for all of the uncovered elements. Subtract this value to all the uncovered elements, and then add this value to the intersection of the lines. Return to step 4. And step 6. Assign the jobs to the workers by choosing an element in the last matrix that has a value of 0. Remember to choose only one 0 in each row and column. Solving assignment problems is very easy. You can even opt to not use the algorithm and just check the problem by inspection. For small problems, e.g., 3x3 or 4x4 cost matrices. The steps shown are only applicable to minimization problems. If the problem requires the maximization of its objective function, you can choose to use any of the following. Step 1. You must multiply -1 to all elements of the cost matrix. After doing this, you can proceed in doing the steps, solving the problem as if it were a minimization problem. Step 2. Construct a pseudo-cost matrix by finding the maximum value in the whole cost matrix and then subtracting all the elements from it. Highest cost minus element x. You can now proceed in doing the steps as if it were a minimization problem. Note: the assignment problem must be balanced, an m by m matrix. You can add dummy points in order to balance an unbalanced assignment problem. Now, let us apply the concepts we just learned through solving this problem. 5 employees are available to perform 4 jobs. The time it takes each person to perform each job is given in Table 1. Determine the assignment of employees that minimizes the total time required to perform the 4 jobs. Note: an x means the person cannot do the job. This can be assumed to a very large value m, which will make the method avoid this assignment. As we can see, the assignment problem is not yet balanced. We have to add a dummy job in order to balance the problem. The dummy job must have 0 time values because it does not really add a value to our objective function. It is just there to balance the problem. Now we have a balanced assignment problem. We can now proceed to step 2. Notice that due to the addition of a new column, the minimum of each row would be the zeros. Thus, the second step is obsolete. We now proceed to step 3, finding the minimum of each column, then subtracting it from the other elements. We can create a minimum of 4 lines to cover all the zeros, as can be seen in the following table. We are not yet done since we only have 4 lines. In order to find an optimal solution to this problem, we need 5 lines that cover all of the zeros. And so we proceed to step 5. The minimum cost in the latest table is 2. We now subtract this value to all uncovered elements and then add it to the intersection of the lines. We return to step 4 by covering all the zeros in the new matrix. We now have 5 lines covering all of the zeros. Therefore, we have found an optimal solution. The following table shows the optimal assignment of the employees to the jobs. And the minimum time is 18 plus 18 plus 14 plus 25, and that is equal to 75 hours. Maximization. To illustrate how the Hungarian method works in solving maximization problems, here is an example. Suppose we have 3 employees, Jane, Janet, and Jean, and 3 jobs for them. The aim is to maximize the products produced by each employee. We are given their production as follows. For this video, we will negate all the elements of the production matrix and treat the problem as if it was a minimization problem. Multiplying -1 to all elements, we will get the following matrix. We can now treat the problem as a minimization problem in order to use the Hungarian method. First, subtract all the row minimum. Now subtract all the column minimum. We can cover all of the zeros using 2 lines. The minimum value from the uncovered elements is 1. We now subtract this value from all the uncovered elements. We can now have a minimum of 3 lines to cover all the zeros. Therefore, we have found an optimal solution to our problem, and it is as follows. And the maximum production in units is 10 plus 2 plus 12, which is equal to 24 units. You can try answering this again by following the second suggestion, constructing a pseudo-matrix and solving maximization assignment problems.